So, we are on the way of discussing magnetic field, and preparation to that we discussed currents, electric currents, especially electric current densities, the volume current density, surface current density, and then we talked about divergence of J, an equation of continuity. We also saw that magnetic field is essentially an relativistic phenomena. Length contraction plays a good role. Current carrying wire which is neutral in one frame, electrically neutral in one frame, may be charged in other frame, and that gives rise to the fact that there has to be a magnetic field. All those things we did. Now, let us do some problems so that these concepts that we have developed, some of the concepts, especially the current densities and the current distributions, because that will be extensively used when we will be doing magnetic field due to different current distributions. So, today we will solve some problems on these concepts, and then we will go ahead with the course. So, the problems are from this my book, Classical Electromagnetism, Bharti Bhavan, and this electric current is in chapter 10, and from there I am writing some problems. So, the first one is qualitative. Which of the following are examples of steady currents? Which of the following are examples of steady current? Now, what is the steady current? Steady current, as we discussed, if the current does not change with time, the current at a particular point, at all points in the space. So, if the current at any given point is not changing with time, then we call it steady current. So, the things are the first one is a ring of radius r, capital R, having a uniform linear charge density lambda naught, rotating about its axis with a constant angular velocity omega. So, you have a ring, and then this is the axis of the ring, and this ring is uniformly charged, uniform linear charge density lambda naught. You know this linear charge density means charge per unit length. If the charges are existing along a line, then you take some dl and then see how much is the charge, then divide, that is called linear charge density, and it is uniform linear charge density. That means the same everywhere. You take this dl here or you take this dl here, is the same, and that is lambda naught, and it is rotating about its axis with a constant angular velocity omega. Okay. So, since the charges are moving, on the circular path, there is a current, and at the site of that circle, that ring, you have charges, and therefore, you have current. If you are somewhere else, not on the ring, then there is no charge, there is no current. So, at places I is 0, current is 0, and at places I is not 0. But then if it is moving with a uniform angular velocity omega about its axis, then outside is always outside, inside is always inside, on the ring is always on the ring, and therefore, if it is 0, it's 0 all the time. If it is not 0, it's not 0 all the time, and the magnitude is also fixed, lambda times V. For a linear charge distribution moving in a line, the current is lambda times V, and lambda is given fixed lambda naught, V will be omega times the radius. So, that is also fixed, and therefore, the current does not change with time, and this is a steady current. Then the next one is a ring of radius capital R with a uniform linear charge density lambda naught rotating about one of the diameters with a constant angular velocity omega. So, the same situation, but now it is rotating about a diameter. That means, it is rotating not about its axis, but a diameter. So, if you draw the ring this way, here is the diameter, here is the diameter, and it is rotating about this. Now, you can see the uniform charge density is there, lambda naught, the angular velocity is also uniform, but at this instant where are the currents located? Currents are located here. Where you have charge, only there you can have current in dq dt, and therefore, the currents are here outside the board. At this instant current is 0, then on the other side of the board 0, current is 0, and current is only here. What happens after some time? This ring rotates, part of it comes out of the board and part of goes on the other side of the board, and therefore, at this instant the charges are here, the current is here, but at a later instant current here becomes 0, on the board it becomes 0, and then this part comes here. So, the current is here. There was no current here, but now it is current here. So, it is not a steady current, the current depends on time. So, the axis of rotation had played a great role. See, a ring of radius capital R having a non-uniform linear charge density lambda, which is a function of phi, rotating about its axis with a constant angular velocity omega. So, it is this situation, but then this lambda is not constant, it is a function of phi. When I am writing phi, I am using that cylindrical polar coordinate s comma phi comma z. This is our z axis. You can take some line as the x axis, and in the xy plane this angle is phi. So, this lambda depends on phi, lambda is different here, lambda is different here, lambda is different here, lambda is different here. So, if I look at this point, let us say here, there is some lambda, right, which depends on this angle. Now, what happens? The ring rotates about this axis. So, the placing is all right, it remains at its own place, it is rotating, but then this portion will come here. This portion which is now here, after some time it comes here, and if the charge densities are different, here and here the charge densities are different, and the current is this lambda V, and V is same, V is omega times R, but this lambda is different here and different here. So, if I am looking at this point, at this instant lambda is different, and then later when this part comes here, lambda is different. So, if lambda is different, current also is different, and therefore, current depends on time, and it is not a steady current. So, that is how you have to check, because it is only the steady currents which will give you the equations for magnetostatics. Now, another question is, a metallic sheet of thickness T has a constant has a current density capital I. So, you have a metallic sheet, of thickness T, small t, has a current density J, has a current density J. If we neglect the thickness and treat the sheet as a surface, the current has to be considered as a surface current. What will be the corresponding surface current density? So, you have this metal sheet, let us say this is your metal sheet, this is the thickness, this is the thickness, this is the thickness, it is a metal sheet like this. This is a, let us say this is a sheet, this is a sheet, of course this thickness is quite large. So, there is a current density, volume current density J. That means, inside the sheet somewhere you take some small volume element d-tau and see how much is the current there. So, you make a cross section and then small cross section, then see how much charge is going from this side to that side, divide by that area and get that J. So, it is like that. So, if I take let us say a cross section somewhere here, a cross section like this, this is the thickness and then I do not know how to draw. So, what I am doing, I am taking some cross section here, I am just taking some cross section here. So, how much is the current, how much current is going from this side to that side? So, that will be J into that area of cross section that I have taken. Okay. So, J into area of cross section. So, if I say that this length is, let us say, a small a, and this thickness is T, okay, this length is small a and this thickness is T, then if I take the cross section, the area of that cross section will be this A into that T, and charges will cross this cross section from one side to the other side. So, the area of cross section here is A into T and the current density is J, and therefore, the current is J into A into T. So, that is the current which is crossing this cross section. So, this much is current, this much is the current which is crossing this cross section. Now, if I neglect this thickness T, this T is very small and I treat this whole thing just as a surface, then whatever was going through that cross section is now going through this line, okay, this line A, length A, thickness T, that made the cross section and the charges were crossing. Now, I am saying that okay, thickness is very small and I treat it just as a surface. So, that whole charge which is going from this side to that side, crossing that cross section, now we will treat it as if it is going through this line, and therefore, you get surface current density, and surface current density is by definition, the surface current density is by definition the current crossing this line divided by the length of the line. Remember that? Remember that K, how do we define K? K is the current which is crossing that length delta L. So, that is the surface current, and here this is the current and that is crossing this length A, small a, because T we are just squeezing it, and therefore, this will be J into A into T, this is the current, and then divided by the length, length is A. So, it is J times T. So, K is J times T. If the volume current is J and I treat the thickness very small and consider it as a surface current, we will describe it in terms of surface current density, and that will have this relation with volume current density. This is K is J times T. Now, next question is, a current flows in a straight cylindrical wire so that an electric field E is maintained in the wire. Now, the next question is, an isolated radioactive source, an isolated radioactive source. Sodium 22. Sodium 22 is kept at the origin, is kept at the origin, is kept at the origin and emits positrons isotropically, and it emits positron isotropically at a rate of 10 power 7 particles per second, at a rate of 10 to the power 7 particles per second. So that is the rate. And consider a spherical surface with the center at the origin. Consider a spherical surface with the center at the origin, and radius 10 centimeter, and radius 10 centimeters. And now the question is, find the current density through the surface. Find the current density through the surface. Find the current density through the surface. So what is all this? You have a radioactive source, sodium 22. Sodium in general has this total number, mass number as 23, 11 protons and 12 neutrons. But if you make sodium 22, then it decays. Sodium 22. Sodium 22 means 11 protons and 11 neutrons. In general, you have 12 neutrons and 11 protons. That's the most stable isotope. But if you make this, the number of neutrons is less and number of protons is more in that sense. From the stability, this should have been 12, so this is less, and therefore one proton will convert itself into a neutron, and this will become what? This will become 10 here and 12 here. And what is this 10? This is neon. Okay, so sodium will convert to neon, that is called beta plus decay, because a proton has converted into neutron, and therefore for charge conservation, you have positive charge here, you have neutral here, you should have a positive charge, and therefore a positron is emitted, and of course some neutrino, that is another thing. So this is the condition. When you put this radioactive source sodium 22, it will keep on emitting these positrons. This is called positron. The charge is plus E. Electron is same as the charge on the electron, but with positive sign, and mass is same as the mass of the electron. This is positron. So is kept at the origin and it emits positron isotropically. Now isotropically means it is emitting in all directions, that emission is same. So it is emitting in all directions with equal number of particles in this direction, that direction, that direction, that direction, that is isotropically at the rate of 10 power 7 particles per second. Now, consider a spherical surface with the center at the origin and radius 10 centimeter. So, radius 10 centimeter, and here is that positron source sodium 22, which is emitting positron in all directions, and then you have to find the current density through the surface. How much current is going? How much current is going through this surface per unit time? Right, these positrons are going this way. So, per unit time means per second. How many positrons? Number of positrons will be 10 to the power 7. Number of positrons times 1.6 into 10 power what, minus 19 coulomb. So, this much charge is going per second. So, this is the current, this is the total current, and then it is going through that 4 pi r square. So, you can divide and get how much is the charge, the current density here. So, you have taken a surface and then from that surface charges are crossing, and you are asking what is the density, the current density there. So, this is how you can get it. Now, the next one is a long thin cylindrical pipe, a long thin cylindrical pipe, a long thin cylindrical pipe of radius capital R carries a current I, of radius capital R carrying a current I going along its length. Okay. The current is uniformly distributed along the surface of the pipe. The current is uniformly distributed along the surface of the pipe. Take the z axis along the axis of the pipe in the direction of the current. Take the z axis along the axis of the pipe in the direction of the current, in the direction of the current. What is the expression for the surface current? What is the expression for the surface current density? Okay, so what is the question? It says a long thin cylindrical pipe of radius capital R. So, you have a thin long cylindrical pipe of radius r. You can take this as a pipe, hollow inside, and then radius is capital R, and it carries a current capital I going along its length. It is a pipe. So, inside is just hollow. So, the current is going on the surface. So, current I going along its length like this. The current is going like this, the total current is I. And then it is distributed along the surface pipe uniformly and all that. Z axis is here, and then we have to find the expression for the surface current density. So, the surface current density is current crossing a given length divided by that length. You have a surface, on the surface you draw a line, and then see that how much is the current through that line, how much charge is crossing that line from one side to the other side per unit time, that is the current divided by the length of the line, that is surface current density. So, here if the total current is I here, so I can take any periphery on this pipe, So, the current is going from this side to that side, and it is crossing this periphery. What is the length of the periphery? 2 pi into capital R, and total current is I. So, the current crossing per unit length, current crossing the line and then divided by length of the line. So, simple, capital I by 2 pi R. K is equal to capital I divided by 2 pi R. And then what is the direction? It is the direction of current, in the direction of current, and everywhere the current is in the same direction, Z direction, and therefore, no doubt it is K cap, total is K cap. Now, the next one is a sphere of radius r r carries a charge capital Q uniformly distributed on its surface, carries a charge Q distributed uniformly on its surface. Okay. If the sphere rotates with an angular velocity omega, if the sphere rotates with an angular velocity omega about the z axis which is taken along one of the diameters, about the z axis which is taken along one of its diameters. What is the current density everywhere? What is the current density everywhere? So, that is the question. So, you have a sphere of radius capital R carries a charge capital Q distributed uniformly on its surface. So, you have a sphere and on the surface of this sphere, that 4 pi capital R square area, a total charge q is distributed uniformly. Then this is rotating about one of its diameter, which is taken as the z axis. This is the z axis, here is the center, and it is rotating with a uniform angular velocity omega about the z axis, which is taken along one of its diameters. So, that is the situation, and you have to find current density everywhere. So, current density is only on the surface of this sphere, because the charges are only on the surface of the sphere. So, take any point on the surface. Remember, it is a surface, half the sphere is outside the board and half the sphere is inside on the other side of the board. So, I am taking this small portion of the surface area somewhere on the surface. So, here how is the charge moving? How is the charge moving? This charge is going in a circular path, right. So, the whole sphere is rotating about the z axis. So, every particle is going on a, if you take that z axis as vertical, then every point is going on a horizontal circle of different radii, If the particle is right here, like equator of the earth, then the circle is this, the radius is capital R, this is the radius capital R. But if the particle is not here, it is here, it is going on this circle, it is going on this circle, then the radius is small. And how much is that radius? If you use spherical polar coordinates, and here is, let us say, your point, or here is your point, then this angle is known as theta. This angle is known as theta from the z axis. Okay? And this theta is same. You take the point here, here. Imagine this is the circle. Take any point, join to the center and see the angle with the z axis is the same, it is making a cone. So, this angle is theta, and therefore, this radius of the circle is r sin theta. And what is the direction in which this charge is moving? That is phi cap direction. In spherical polar coordinates, if you take some point, drop a perpendicular, then join here, and with the x axis the angle is phi, and this is like this perpendicular, I am drawing perpendicular. So, you have this plane is making angle phi with that xz plane, alright. So, when phi is changed, what happens? This point goes along that circle. So, at one point it will be phi equal to 0, which is just above the x axis, phi is 0, and then as you rotate it in that horizontal plane, phi changes from 0 to 2 pi, and therefore, the direction in which phi increases, that is called unit vector phi cap. So, this velocity is in the direction of phi cap. Here phi cap is like this, tangent here. Here phi cap is this tangent, here it 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 is this tangent. All these are phi cap directions. They are different directions. The phi cap here is not the same as phi cap there. In Cartesian, I cap, j cap, k cap, they do not change directions wherever you take your point, but spherical polar coordinates, yes. So, the velocity is omega times the radius, which is r sin theta, right, v equal to omega r. Your formula is v equal to omega r. This is the radius of the circle, here is the radius of the circle, and angular velocity, multiply, you get the linear velocity v, and in what direction? In phi cap direction, So, what is the surface current density? the surface current density is sigma V, and therefore it is sigma omega r sin theta and phi cap. J, volume current density is rho times V. The charge density, volume charge density per unit volume, how much is the charge, that is rho, and then you get volume current density. And if you have surface charge density sigma and then the velocity is V, then you get surface current density K is sigma times V, and V is this, so it is this, and hence this is Q by 4 pi capital R square, that is sigma omega r sin theta and then phi cap. 1 r you can cancel, and that is your answer. The current density at the surface of this sphere is this much, Q omega sin theta divided by 4 pi capital R and then phi cap. This theta is variable, which point at different points you have different current densities. This theta is variable. Magnitude, direction also changes, phi cap tangent to that velocity. So, that is the current density.